Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about the end of Chapter 7. I know this is Part 3, so if you haven't seen the first two parts, you probably want to go back and try to find those two. I'll put them in the description also, but we kind of left off with periodicity, and so I combined a little bit of parts of Chapter 8 with Chapter 7. So the periodic trends that Section 7.12 goes over are specifically atomic radius, ionization energy, and electron affinity. There are two other atomic trends, electronegativity and ionic radius. Those are covered in Chapter 8. So I kind of stole some of Chapter 8 to put in here because I thought it would be better to put all of the periodic trends in one and in one presentation rather than separate them out. So I'll touch a little bit when I do my video on Chapter 8 from Zumdahl, a little bit about these, but I'll kind of assume that you watched the previous, chapter before going over Chapter 8. So let's talk about atomic radius. So what is atomic radius and what's the trend? So the first thing that you need to be aware of is the fact that the atomic radius is, if we have like a center point in the middle of the nucleus of the atom, the atomic radius is going to be measured from the center of the nucleus all the way to where that furthest electron is. And so you can imagine kind of making an imaginary sphere from from the center to here. That would be the radius, and then you can basically turn that into a three-dimensional sphere. And that's kind of what the atomic radius is. So what's the pattern as we go across the periodic table? So in general, as we go across a period from left to right, so that means that we go this direction, the atomic radius decreases in size. And again, we're speaking generally. There might be a couple of exceptions, but again, on the AP exam, we're assuming broad periodic trends. Okay, we're not going into the exceptions or anything like that. And so why does that happen, though? Because most of the time people would assume, oh, as you go across and have more protons, the atom should get bigger and bigger and bigger. Because as you have more protons, you also have more electrons. But in reality, the reason why we have a decrease in size as we go across is because the effective nuclear charge is increasing. And the effective nuclear charge is literally just the number of protons in the center of your nucleus, right? And you can and the effect of the other core electrons that are shielding it. But the effective nuclear charge is getting bigger and bigger and bigger as you go across the periodic table. But there is kind of something that ends up decreasing the size of the atom, and that is the fact that the valence electrons, so the electrons that are furthest away from the nucleus, as you increase the number of protons, you're actually going to then have a stronger pull on those protons towards the valence electrons that are going along the outside orbitals of your atom. So that means that you're actually going to get those electrons pulled closer and closer to the nucleus as you go across a period on the periodic table. And so because of that, we have a trend in atoms getting smaller and smaller as you go across. In general, as we go down a group, the atomic radius gets larger and larger. So as we go down a period, so pick any column you want, as you go down, you actually end up getting a larger and larger atom. And so the reason for that is because orbital sizes increase, because not only are you might think, oh, isn't the effective nuclear charge increasing a lot more as we go down? Yes, that is totally true. But remember, as we go further down the periodic table, we're actually adding larger shells along the outside where the valence electrons are. So in reality, going down from one column to going down to the next one, that's going to create a huge difference in the size of the atom itself, because now you're gaining an entire orbital. And so you can see that pictured if we remove all of the transition metals here in the little chart that we have. So you can see that hydrogen, 37, and I believe this is in picometers. Helium is 32. And that's because even though as we go across, you're increasing the amount of effective nuclear charge, you also have a stronger pull on those valence electrons in your helium atom than you do in hydrogen. Same thing here, lithium, beryllium, you can see as we go across, it gets smaller and smaller. Neon has the highest effective nuclear charge in this row, but also it's able to now hold on to its electrons a lot more firmly because of that. And again, as we go across, we can see this general pattern. Now, are there exceptions? Yes, there are exceptions. I mean, when we go from gallium to germanium or from fluorine to neon, here they're the exact same, and here, we go actually down one. Here, neon is slightly bigger. And so just keep in mind that yes, there are exceptions, but in general, we're talking about the trend. So that means that if we were to look at this from far enough away, you can generally see as we go down, things are getting bigger. And as we go across, things are getting smaller. Okay. And so don't worry about like understanding and knowing all of the exceptions. That's not what the AP exam is all about. All right. So which should be the larger atom and why? Sodium or chlorine? So you probably want to look at a periodic table, but even if you don't have one, you might think, okay, well, sodium, and you're correct. So sodium has a smaller effective nuclear charge and chlorine has a larger effective nuclear charge. Notice that both sodium and chlorine are in the same period. So it's easy to compare the two to each other because they have the exact same sort of valence electron energy level here. We've got, the 3s, we've got the 3p, they're still in the 3s. So that means that, again, we're comparing basically apples to apples here. And we're not picking something that's in a completely different location on the periodic table. So I can say because sodium has a smaller effective nuclear charge, it's not going to hold on to its electrons with as much gusto as chlorine will, because chlorine has, again, a higher effective nuclear charge. What about lithium or cesium? So cesium is going to be larger. It does have more electron shells. So again, now we're comparing things that are in the same column. So now the effective nuclear charge isn't the big thing to bring up. Instead, it's the fact that we have more electron shells. So lithium's right here in the 2s for its valence electrons, sorry. And so you can tell that it only has 2 shells around it. But here, when we get to cesium, it's 1, 2, 3, 4, 5. It's in the 6th row. So that means that it has 6 shells. All right, so now here's an interesting question that I like. Which is larger, the hydrogen's 1s orbital or the lithium's 1s orbital? So again, we're talking about that very first energy level that can have up to 2 electrons in it. Which one do you think would be larger? Would it be hydrogen's or lithium's? And so the answer is hydrogen's. And there's a reason for that. Lithium has a higher effective nuclear charge. It has 3 protons. Hydrogen only has 1. And so it's going to actually have a lot stronger of a pull on the electrons that are in the 1s orbital. So its core electrons are going to get held a lot closer than hydrogen's would. Now, what makes lithium larger than hydrogen then, right? Well, it also has a whole other energy level. It has a 2s energy level with an electron in it. And so because of that extra shell, lithium is a lot bigger. But its 1s orbital is actually held a lot closer to the nucleus because of all of those extra protons that would hold those 2 electrons a lot closer. Hydrogen, on the other hand, has a single electron anyway and a single proton. And so its 2s level isn't even filled with anything. But I always like this question because it makes you kind of think of all of the things we just talked about. What about ionic radius? So remember, ionic radius is actually in chapter 8, but I wanted to kind of put that together here because I thought it kind of fit better. So something to keep in mind, cations. So cations are positively charged ions. They are smaller than their original atom. And there are reasons for that. The first general reason why, and there are 2 possible reasons, is because there's less electron-electron repulsions because cations lose electrons. So cations have a positive charge because they've lost electrons to begin with. And so because they've lost electrons, there's going to be less electron-electron repulsion, meaning that you're not putting electrons necessarily next to each other anymore. And so that would mean that they would have less repulsion. Another general reason is because sometimes metals will lose an entire electron shell. So you can picture if you have a 3s energy level and you lose it, what's the next closest thing? It's the 2p. And so the 2p energy level is a lot closer to the nucleus than the 3s would be. And so anions, so these are the negatively charged ions, they're much larger than their original atom. And the reason why is because if you add more electrons to something, that's going to generate more electron-electron repulsions. And so because of the extra repulsion, that's going to inflate their size. And so you can kind of see that here. So this is a lithium atom versus a lithium ion. So it almost cuts it in half. In fact, it cuts it more than in half. What am I doing math-wise? Here you can't really see them very well, but chlorine is tiny. Chloride ions are way, way, way bigger. Same thing here. You've got fluorine, the atom, 64 picometers. Fluoride, the ion, is over double. And so that's true of, again, positively charged ions. They're always going to be smaller. Negatively charged ions are always going to be bigger compared to their original atom that they came from. Now, electronegativity, again, this is from chapter 8 also. It's chapter 8, section 2, I believe. So what is electronegativity? So electronegativity, the way I look at it, is it refers to how strong a nucleus attracts electrons from another atom. Now, in general, the trend is as you go from left to right, it increases. So as you go from left to right across the periodic table, the atoms get better and better and better at attracting electrons to themselves. Now, the notable exception to that are generally the noble gases. As you get closer to the noble gases, though, it does require fewer electrons to fill the outer orbitals. So that means it will require less energy to attract electrons from another atom. That's the reason why, as you go from left to right, this trend occurs. Now, what about the noble gases? Why are they an exception in this? The noble gases already have full valence electron shells. So they don't want generally more electrons because they already have a full outer shell. There are exceptions, but again, we don't care about the exceptions. We're just going over the broad general trends here. So in general, as you go down, electronegativity gets worse and worse. So it becomes harder for an atom at the bottom of the periodic table to try to attract electrons than something that's higher up the periodic table. The reason why is because atomic size increases as we go down, right? So as you go down, you're getting bigger and bigger and bigger atoms. So therefore, the nucleus is further away from those valence electrons, making it more difficult for them to attract electrons to themselves. So electronegativity, another little fact to learn is that fluorine is the most electronegative atom on the periodic table. So you can kind of picture it like this. As you go towards fluorine, you get higher and higher and higher values for electronegativity. Now, this chart might not look exactly like the one in the book, and it might not look exactly like the one that you find online. That's because to measure the electronegativity, it's called normally the Pauling, the Linus-Pauling electronegativity values. They do change. And as you get better data, they do update these values quite frequently anyway. But you can see again that if we pretend that krypton and xenon don't exist here, then all of these right here would have basically a 0 for electronegativity. Now, if you're wondering why krypton and xenon don't have, zeros for electronegativity, instead they have higher values, there's not really, I can't really go into detail of that. That's way above like what AP chemistry goes over. I can tell you that generally though, krypton and xenon do form compounds, unlike helium and neon, which don't. So you can kind of think of it this way, that these two do form compounds. Like normally we think of noble gases as not forming any compounds, but these two do form compounds, whereas the higher ones up here don't. Okay, what about ionization energy? So back to actual chapter 7 stuff. So what is ionization energy? So ionization energy is the energy that is required to remove an electron from a gaseous atom or ion. So you can picture this is our, atom or ion. Well, in this case, it's an atom. And I'm trying to remove an electron from it, and now it is turning that into a positively charged thing. So that's what ionization energy is all about. And so you can say right here, like for magnesium, to remove a single electron, it takes 735 kilojoules per mole. And then if I wanted to remove a second electron, it would take 1,445 kilojoules per mole. And then you could continue if you wanted to remove 3, if you wanted to remove 4, etc. So notice, though, that magnesium here is in the alkaline earth group. So it's in the second column. More on the alkaline earth group in a bit when we actually go over that stuff. But the idea is that magnesium generally loses 2 electrons. So notice that the ionization energy to remove 1 versus to remove 2, not crazy different. But if I wanted to remove a third, there's a huge jump. And the reason why is this third electron is actually one of those core electrons. And so it is bound much more tightly than any valence electrons are. Remember, valence electrons are the ones where the interesting chemistry happens. They're the ones that are on the outside of the atom. Now, what's the trend in ionization energy? So in general, as we go across the period from left to right, the ionization energy increases. And so you can see that as we go across here, in general, again, are there going to be exceptions? Yes, of course there are going to be exceptions. But you can see that I'm getting darker and darker as I go across, and as I go down, I'm getting lighter and lighter. Now, why exactly as we go across does the ionization energy increase? And so here's the reason why. As we go across, electrons are added, generally speaking, in the same shell. They do not completely shield the increasing nuclear charge caused by adding a proton as you go across, a row on the periodic table. So generally speaking, electrons in the shell are more strongly bound from left to right on the periodic table. So you can kind of see this when we go from here to here. And that's because, again, we're adding an electron to the same shell. In other words, again, this is the 2s energy level. This has 1 electron, this has 2. And so we have a shielding issue as we go across. And so if I wanted to remove an electron from here, it's going to be a lot easier than if I want to remove an electron from here, because now we have 2 electrons that are in the same energy level. And then as we go across, you can see that kind of increases, and I cut off the noble gases, but you can imagine to remove an electron from a noble gas is going to take a lot of energy. All right, so in general, as we go down from top to bottom, the ionization energy will go down. It will get easier. Why? Electrons are being removed from an area that is on average further away from the nucleus. So remember, as we go down, electrons are getting further and further away because we're gaining extra electron shells. And so that means that if I'm going to remove an electron from something, it's going to be a lot easier to remove it from something that's bigger. The further away the electrons are, the more shielded they are from the effective nuclear charge in the center anyway. So it's going to be a lot easier to do that. Now, what do these values look like? So if we were to graph them, it looks a little sporadic, but you can start to see patterns. So again, you can see hydrogen, and then I go all the way to the other side of the periodic table to helium. And then I'm going back to, lithium is underneath hydrogen. So I'm going back to where hydrogen kind of is located, just underneath it. And then I go to beryllium, and then it goes up. Okay, now what's happening with boron and carbon and nitrogen and stuff? So now I'm going across to the opposite side of the periodic table to get to boron. That's why there's this little exception here. Then I go to carbon, I go to nitrogen. Okay, great. Why is nitrogen, when I get to nitrogen, why does it drop down, when I get to oxygen? Well, remember that we have in a p orbital, we have 6 electrons we can fit. And remember, according to, whose rule was it? Hund's rule, right? I have to spread out my electrons before I start filling them up. And so notice that pattern exists. Boron, carbon, nitrogen, now I have all of them spread out. And now I'm starting to pair them up. Oxygen, fluorine, and then neon. And you can see that repeated over and over again. So like it says, where are the exceptions? And what's going on here? Why do these exceptions exist? And so it is because of electron repulsion. And so you can see right here, like I just explained, from beryllium to boron, there's an exception. From nitrogen to oxygen on this graph, there's an exception. And again, it's all because of electron repulsion. You're now moving to a different section kind of the periodic table in this section between beryllium and boron. And then you get to nitrogen and oxygen. Now you're pairing up according to Hund's rule. You're now pairing up electrons, and so that's going to create some extra repulsion. So which atom would require more energy to remove an electron? Sodium or chlorine? Answer, chlorine. Chlorine has a much higher effective nuclear charge. It's going to require way more energy to remove an electron from chlorine than from sodium. And again, we're comparing them because they are, again, on the same side of on the same row of the periodic table. And so you can see here that chlorine is ridiculously high. Sodium's on the opposite side, and I cut it off, so you can't even see it. What about lithium or cesium? So answer, lithium. Lithium has outer electrons that are more tightly bound. Cesium is gigantic. And so again, lithium's right here. Cesium's all the way down here. So it requires 520 kilojoules per mole. For cesium, it's only 375, which would have the largest second ionization energy. And why? Lithium or beryllium? Answer, lithium. Why? Well, beryllium is in the second column, so it is okay losing 2 electrons. Lithium, on the other hand, only has 1 electron in its valence shell. So if you want to remove a second electron, you're going to have to remove a core electron. And anytime you try to remove a core electron, it's going to take way more energy. And again, we have lithium here and beryllium just for that visualization. Lithium only has 1 valence electron. If I wanted to remove a second one, it would only have 1 electron left, making it like basically hydrogen in that case, right? A 1s1. Beryllium, on the other hand, has 2s2, and so to remove those 2 electrons is going to take a lot less energy because it's not a core electron that you're removing. And again, that pattern, you can see them. You can see the huge jump when you're trying to remove core electrons. So you go from 2,700 something to 11,000 kilojoules per mole. It's a pretty big jump. Right. What about electron affinity? So electron affinity is energy, an energy change that is associated with adding an electron. So electronegativity is removing an electron. Electron affinity is adding an electron. And again, we're talking about gaseous atoms here. So we have, again, a gaseous atom. We are going to be adding an electron, and it's now going to have a negative charge to it because we added an electron to it. So in general, as we go across, electron affinities become more negative. That is because they become more positive as we go down. Sorry, that is because. In general, as we go down, they become more positive. And so you might think, and so here's a little clue, that fluorine would have the highest electron affinity, though. So that does seem to give you the idea that, oh, this is kind of like, electronegativity. It's just now kind of reversed, let's say. So you might think that fluorine would also have a high electron affinity, but actually it's chlorine that has the highest one. And why is that? Okay, well, to explain this, it's again a little bit more complicated, but I'm trying to do my best. So fluorine is just too small, and the electrons are so close to the nucleus still that they're going to basically repel each other. Now, keep that in mind that when we're talking about strong versus weak acids later on, electron affinity will come back. Okay, so this is like several chapters later. But I like to kind of add this as a little reminder because a lot of times people wonder, why is hydrofluoric acid a weak acid? And part of it, when hydrochloric acid is a strong acid, and part of the reason why it has to do with electron affinity. So again, electron affinity, you can see that as we go across here, it looks like fluorine should be, the one with the highest, but it actually is chlorine. Chlorine just edges out fluorine because of this weird kind of little fact. But generally, as we go down, you can see that they get smaller. And as we go across, things are getting larger and larger. Again, in general, are there exceptions? Of course. So let's arrange these elements from, so we have oxygen, fluorine, and sulfur, according to increasing ionization energy. All right, let's see if we can put them in order. So we've got sulfur, oxygen, fluorine. So again, you can see that in general, again, as we go across, we're increasing ionization energy, and then sulfur is on a whole other level, right? It's further down, so that's going to create a problem for us and make it automatically the lowest. What about atomic size? So again, fluorine is going to be the smallest because now we have kind of the opposite pattern. And then as we go further left, things are getting bigger. So oxygen's getting bigger, and then definitely as we go down a column, sulfur is in a whole other field, let's say, because it has a whole extra electron shell around itself than the other two do. So let's talk about the periodic table in general now. All right. So hopefully what you've learned over the course of this entire chapter, which has taken 3 parts in order to finish, that the number and type of valence electrons that you have determines an atom's chemistry. And so electron configurations can be used to determine how the periodic table is organized altogether, which is kind of cool. Certain groups, though, on the periodic table do have special names, and we'll talk about them. And so let's talk about those special names. So we have the alkali metals that are in the first column here. Notice hydrogen is not an alkali metal, because first of all, it's not a metal. And second of all, It's not alkali. So right here, we have the alkali metals. Second column, alkaline earth metals. That huge D block right here in the center, those are the transition metals. Technically, lanthanides and actinides are the F block here, lanthanides being the first one and actinides being the second one. Are they transition metals? Generally speaking, yes, they're normally considered transition metals. They normally have another weird little name. They'll call them like rare earth metals or something, but for our sake, just know that transition metals are the D block, lanthanides and actinides are the F, but technically they're transition metals in my head. Halogens are, it says group 7A. Normally I call that group 17 because normally I count 1, 2, 3, etc. going across. Noble gases are 8A or group 18. Now let's talk about them. Alkali metals, what do they have in common? They have one valence electron. They are low density for metals. Some of them will even float in water. Now, would you want to float them in water? Probably not. They all react very violently with water. And as you go down the group, the reactivity will increase because that single electron is more weakly held. So cesium is way more reactive than lithium is. And again, we're talking about these elements right here on the periodic table, not hydrogen. What about the alkaline earth metals? Well, they have two valence electrons. They're also low density. Most of them react with water, but not nearly as violently as the alkali metals. And they require more energy to remove the two electrons. And so because it requires more energy to remove two electrons, they don't react as readily with water as a result. And so again, we're talking about column number 2 here. Transition metals, they usually have between 1 to 3 valence electrons, but this varies. They can have 4, they can have 10. All right, all of them are solids though, except for mercury, which is a liquid, okay? The density of these metals tend to be very high. In fact, the most dense metal on the periodic table is found in the transition metal group. Most of these compounds, so like if we're looking at compounds that are formed from transition metals, they have distinctive colors. For example, like copper compounds tend to be blue or green. I almost said copper compounds tend to be red. That would have been super bad. Iron compounds tend to be red or orange. They have distinctive colors when they form their compounds. And again, we're talking about this little D block group right here. Halogens, they have 7 valence electrons. They have solid liquids and gases all in there. They're very low density, and they sometimes have the most reactive elements, some would say, on the periodic table. So fluorine and chlorine and even bromine are extremely reactive. And they have very high electron affinities and very high electronegativities. And they're again right here, the second to last column. What about the noble gases? Noble gases have 8 valence electrons except for helium, which has 2. Taller gases. It should say aller gases. I have to fix that. They have low densities. I mean, they are gases after all, right? And all of them are colorless. They don't generally react with things, but if you pass electricity through them, you can get some cool colors. And so noble gases are kind of known for that. And again, they're the last group. All right, so what about metals versus nonmetals? So in general, if we're looking at the periodic table, you can see that almost all of the nonmetals are found on the right side of the periodic table, and they actually form this little zigzag line pattern that separates the metal side from the nonmetal side by these metalloids. So nonmetals are all in pink here, and the only exception to that is hydrogen. Hydrogen, in fact, sometimes you'll see hydrogen moved over here, just to kind of show, okay, it's a nonmetal. Now, metals, on the other hand, are all the gray ones, and so they're literally most of the periodic table. Most of the periodic table is made of metals. The lanthanides and actinides are also metals, but they're not included in the diagram, but just keep in mind they're also metals. The metalloids, now, depending on your book, people include different metalloids, but in general, they are all of the ones that are touching this little zigzag line as we go down. Okay, and so notice that if we are drawing a zigzag line, though, going across, aluminum is a metal. And I know none of these have, symbols on them or whatever, but still, I just wanted to point that out. All right, so let's talk about metals. What are the metals like? So all metals are found to the left of the zigzag line on the periodic table. Hydrogen is a nonmetal, though, so keep that in mind again. What do metals behave like? So metals tend to be solid. I mean, there are, well, I guess there's only one liquid one at room temperature, right? So mercury is the only liquid one, but they tend to be solid. They tend to be good conductors, and that means good conductors of both electricity and heat. There's a reason why we use metal pots and pans to cook things. They're malleable. Malleable means that they can be flattened without really breaking for the most part. Lustrous means that they're shiny, and most people know that metals are shiny. And they react with acid. Now, some have to be reacted with very strong mixtures of acid in order to have a reaction. But generally speaking, if you add a metal to acid, it will start to foam. It'll generate some heat. You'll get bubbles of gas. And yeah, so metals tend to have these properties. What about nonmetals? So nonmetals, except for hydrogen, are found to the right of the zigzag line on the periodic table. They tend to be polar opposites. They tend to be gases. I mean, bromine is a liquid, though, so there is an example of a liquid one at room temperature. And if they're not gases, they tend to be very weak solids, like sulfur. You can break it apart with just your fingers. They tend to be bad conductors. They don't conduct electricity or heat well. They tend to be brittle, meaning that they are easily broken or breakable. Again, you can't really describe a gas as being brittle, but the solids tend to be very weak, so they're very brittle. They tend to be dull, they're not very shiny, and they tend to have low densities, meaning that either they would float, quote unquote, in water, or if you're a gas, like you are going to probably not be very dense anyway. Now, what about the metalloids or semimetals? So metalloids and semimetals, they're interchangeable terms, and you'll see both. Again, they are all of the elements touching the zigzag line with the exception of aluminum. And they tend to have properties that are a mix of both metallic and non-metallic features. So they're semiconductors, which is why they tend to be used in computing devices. Like, silicon is an example of a semi-metal. They tend to be semi-lustrous, so they're not as shiny as metals, they're not as dull as non-metals, they're somewhere in between, and they tend to be malleable. So they tend to be being able to be flattened without breaking. And that takes us to the end, finally, of chapter 7 in Zumdahl, the 7th edition. So again, thank you. If you haven't already, please subscribe and like this video. And I will upload chapter 8 as soon as possible.